Okay, so in this video tutorial, we're going to be talking about horizontal projectile motion for the AP IB Physics Year 1. So one of the results from the activity that you did for projectile motion is figuring out that the horizontal motion is constant and the vertical motion is accelerated. And the general thing that we say about this is that the two directions are independent of each other. So in other words, what I could do in the x is completely independent of what I'm doing in the y. So I can translate our fourth equation to both a x direction, and I could also make it a y direction. So my y displacement is my initial velocity times my time plus the 1/2 at squared. So now what's interesting about this is that if I look in the horizontal direction, the velocity is constant. Another way of saying that is my acceleration is 0. So this whole second part of the term cancels out. And then in the vertical motion, my velocity is accelerated. So I have some initial velocity, and then my acceleration will be my acceleration due to gravity, g, of negative 9.8 meters per second squared. So when I'm looking at this cannon, we know that it's originally 125 meters high off a cliff, and it's launched with a horizontal speed of 10 meters per second. So if I set up my given information, I want to separate what's going on in the x and what's going on in the y. So in the x direction, my v0 is 10, my acceleration is 0, and in the y direction, my initial velocity is 0. And I want you to take a step back and think about what that means. If I draw a velocity vector on this cannonball, the instant it is fired, it is only moving in the horizontal. So in other words, it's not moving in the vertical. And that's where the initial velocity of 0 comes from. My acceleration is a negative 9.8 meters per second squared. And what we want to do for this object is plot where it will be at these various times. So after 0 seconds, it didn't move left or right. It didn't move up or down. So these are both my positions, my x position and my y position, so in meters. And if I kind of scroll down here, you can see that a little bit better. So in the x direction, it's actually pretty easy. In the x direction, my delta x would be my initial velocity, which in this case is 10 meters per second, times the time. So I want to know how far it goes after 1 second. And so I can take a look, and just 30 times 1, 10 times 1 is 10. So after 1 second, it goes 10 meters. After 2 seconds, 20 meters. After 3 seconds, 30, 40, and 50. Now in the y direction, since it's going to be falling downward, my position that I travel here is going to be the initial velocity, which in this case, for a horizontal projectile, the initial velocity is 0. That's actually the definition of a horizontal projectile. And then my vertical position is just negative 9.8 meters per second squared times 1 second squared. So this works out to be approximately 5 minus 5 meters. So after 1 second, it falls down 5 meters. After 2 seconds, 2 squared is 4. 4 times a half is 2. 2 times approximately 10 is minus 20. We could do the same thing for 3. 3 squared is 9. 9 times a half is 4.5. 4.5 times approximately 10 is minus 45. 4 squared, 16. 16 times a half is 4. No, it's going to be 8. And then 8 times 10 is 80. And then the last one would be, you could actually see, is like around 125. So if this object starts off, and actually I could scale this, this would be every dash I can make 5 meters. So this is 5, 15. Actually, let's go. This is 120, 110. This is 100. I'm going to skip a few here. Actually, here 90, 80, 70, 60, 50, 40, and so on and so forth. So after 1 second horizontally, and I'm going to make each dash here 10 meters, that it goes 10 meters here, so and then falls down one dash, 5 meters. The next second, it travels another 10 meters, but then in this case, it falls down for a total distance of 20, so it would be somewhere at 100. So 102 seconds later. And then after 3 seconds, it travels 30 meters, but it falls down 45. So 45 away from this would be at 80. And then we have minus 80, so we're at 45 meters, which would be right here. And then it would be right on the ground. Now what's kind of neat about this is that I could show that with my velocity vector. I could show my horizontal velocity staying the exact same length, and then my vertical velocity getting faster. So my vertical velocity starts off at 0, then gets to some little number, and then gets a little bit bigger, a little bit bigger. I'm going to get too big here. And then at the end, it's some really big value. Okay, so I could actually show, and then actually the way we add vectors, right, is connecting them to the tail. So the velocity vector would be going off at an angle in that direction. It's hard to make a straight line on here. So that's actually how we can kind of map where this object will be during the whole time. And notice that all we're doing is applying these two ideas, that the velocity is constant in the horizontal and it's accelerated in the vertical. So we're basically doing two independent calculations to get its horizontal position and its vertical position. Now notice that the one common link between the two variables is time. And that actually has to do with the fact that time is a scalar. So time is the only piece of information that will fit the two. So time goes between the two columns. So let's do another example down here, and then you're going to do the example on the back. So if we list what we have, so we set up an XY chart. What's going on in the X, what's going on in the Y. So an arrow leaves a level bow at a speed of 45 meters per second. Now if it's a level bow, then this velocity, the 45 meters per second, that's going to be my initial velocity, but it's all in the horizontal. Okay, the height is 1.5 meters. So my height, I'm going to write it as just as h, but that's a vertical distance, is 1.5 meters. We know the initial velocity in the vertical is 0. We know the acceleration in the horizontal is 0. We know the acceleration in the vertical is negative 9.8 meters per second squared. And so the first question is how much time? So time is our unknown in this first problem. So if I look at my given information, what I notice is that I actually have more information in my vertical. So that kind of gives me a clue that, you know what, I'm gonna use this to figure out the time. I have 3 pieces of information. 3 is the magic number in order to figure out a fourth. So I have a height, which is a vertical distance. Okay, I have a initial velocity and I have acceleration. So I can use the equation delta y is equal to v naught t plus 1/2 a t squared. And since I'm just working in the vertical, okay, and trying to find time, My initial velocity is 0, so that term cancels out. So we have delta y equals 1/2 at squared. If I multiply both sides by 2, that gets rid of the 1/2. I divide by a, and then square root. So I get t is equal to the square root of 2 times 1.5 divided by negative 9.8. Now what you'll notice here is that we have negative in the radical, and that can't happen. So we have to apply the idea that this change in vertical displacement is a vector, and the bow is traveling in the downward direction, so its displacement vector is negative. And if you work that out, I got a time of 0.55 seconds. Now, how far away will from the archer will the arrow land? So now I'm looking for a horizontal distance. So now I know how much time it has, but what is interesting is that's how long it takes to go horizontally, and it also is how much time it takes to go vertically. So I'm still going to use the same equation, just in the horizontal direction, but the term that cancels out is the acceleration, since we have this idea right over here that the acceleration is 0. So now I have the initial velocity of 45 meters per second, and I'm multiplying that by my 0.55 seconds. So I get a velocity of I had a distance of 24.8 meters. Now, if I want to know how fast it'll be going in the horizontal just before it hits the ground, well, that's a conceptual exercise. If we look up at above, what we said is that the horizontal motion is constant. So if I know how fast it left the archer, then I know how fast it landed. So it's still traveling at the 45 meters per second, and we can kind of make the argument, since the acceleration in the x direction is 0. Now the vertical speed, I'm going to try to find the final velocity in the vertical. And I know how fast it's picking up speed. In other words, I know what the acceleration is. That's the 9.8, and the initial velocity is 0. So I have negative 9.8 meters per second squared times the 0.55 seconds. And so notice this will be a negative value. Okay. And I got that to be 5.4 meters per second, and it's negative. So now if I want to figure out its overall speed, it is going 45 meters per second this way. This is our good old vector addition, and it's going 5.4 meters per second in this direction. So its overall speed is going to be the hypotenuse of that triangle. So I'm going to have to do a squared plus b squared equals c squared. And when I work that out, I got 45.3 meters per second. Okay, so why don't you take a look at the second problem for now, try that out, bring it into class tomorrow, and we will compare answers. All right, so that's all for today. Have a good night, and we'll see you tomorrow. Bye-bye.